Section 1 Introduction. Our aim in this research paper is to address two primary questions related to the rapidly expanding body of research on large language models, LLMs. First, we want to identify the challenges that remain unresolved in this field. Second, we intend to explore the various areas where LLMs are being applied and understand how these unresolved challenges are affecting their applications. We have categorized the challenges faced by LLMs into three broad areas: design, behavior, and science. On the application front, we have explored diverse fields like chatbots, computational biology, computer programming, creative work, knowledge work, law, medicine, reasoning, robotics, and the social sciences. This paper provides an opinionated review of the topic, assuming that readers have a basic understanding of LLMs and their workings. We primarily focus on models that are trained using text data and target a technical researcher audience, leaving aside any political, philosophical, or moral discussions on LLMs. A significant challenge faced in the field of LLMs is the unfathomable size of the pre-training datasets. One of the primary methods to enhance the general-purpose capabilities of LLMs is to increase the volume of pre-training data. However, the size of these datasets has become so large that it is beyond the capability of human teams to manually check their quality. In lieu of manual quality checks, most data collection procedures rely on heuristic methods for source selection and data filtering. We have noticed certain adverse effects of these heuristic methods, mainly stemming from the fact that many practitioners only have a vague understanding of the data used to train their models. We call this problem unfathomable datasets. One of the issues associated with these datasets is the presence of near duplicates. These are similar data entries that aren't exactly the same but could affect model performance. These are difficult to identify compared to exact duplicates, which are usually filtered out in standard data collection pipelines. Studies have shown that a considerable percentage of tokens produced by a model unprompted are part of a memorized sequence from the training data. For instance, in one dataset, a 61-word sequence was found to be repeated over 61,000 times. Techniques have been proposed to reduce this issue, such as deduplication, which can decrease the rate of omitted memorizations. Further, techniques have been introduced to identify semantic duplicates. These are data entries that may appear different but carry similar meanings. These methods have shown improvement over standard deduplication techniques. Likewise, near duplicates have been discovered in other datasets through the method of clustering document embeddings and identifying clusters that gather duplicates. Section Summary. In this section, the authors address two questions: the challenges that remain unresolved in the field of language model, LLM, research, and the current applications of LLMs and how these challenges are constraining them. They categorize the challenges into three broader categories: design, behavior, and science. One of the major challenges discussed is the issue of unfathomable datasets, where the size of pre-training datasets has outgrown the ability of human teams to manually quality check them. The authors propose methods such as near-dup and sem-dedup to identify and filter out near duplicates in the data, which can degrade model performance. Section: Benchmark data contamination. When we talk about benchmark data contamination, we're referring to a scenario where the training dataset includes information that is similar or identical to the evaluation test set. This overlap might inflate the model's performance metrics because it could simply memorize and then restate the test data during evaluation. In real-world applications, identifying and eliminating such overlaps between training and testing data is quite challenging. As a case in point, the creators of GPT-3 encountered a software glitch after they had finished training their model. This bug meant they were only able to remove a portion of the identified overlaps from the training data. It was too costly to retrain the model, so they proceeded with the existing overlaps and tried to mitigate the issue by creating clean versions of the benchmarks, removing any potentially leaked examples. To identify these overlaps, they set a rule: any example that shared 13 consecutive words or more with any other example in the pre-training set was deemed to be overlapping. If an example was shorter than 13 words, it was considered overlapping if it was identical to another example in the dataset. The team also looked for test data within the web-crawled C4 corpus, a dataset widely used in NLP. They looked for exact matches after adjusting for differences in capitalization and punctuation. This investigation revealed various forms of contamination, including instances where both the input and label were contaminated in text generation and knowledge completion tasks, and instances where only the input was contaminated in the glue benchmark. Their analysis showed that test data could find its way into a snapshot of Common Crawl, the original source of the C4 dataset, in two ways. Either the test set was built using text from the web, or the test set was uploaded to the web after it was created. They asked ChatGPT to generate examples of academic benchmarks and found that it had memorized several, including some from the test sets. To mitigate this contamination, they proposed 3 strategies, including the use of encryption and training exclusion controls. The other issue raised in this text is the presence of personally identifiable information, PII, such as phone numbers and email addresses, within the training data. Instances of such PII have been found within pre-training datasets, leading to potential privacy leaks. For instance, it was reported that PII data could be extracted from GPT-2 by prompting it in a specific way. There was also a case where an engineer was able to obtain secret API keys by prompting GitHub Copilot, a code-writing AI tool. The presence of PII in legal data across different jurisdictions was also discussed. The researchers suggested filtering this data based on the legal standards of the respective jurisdiction. The problem is that for a model to perform well, it often needs to memorize its training data, so if PII is present and not detected in the training data, it is likely that the model will reproduce this information, potentially causing privacy issues. Section Summary. Benchmark data contamination occurs when the training dataset contains data similar to the evaluation test set, leading to inflated performance metrics. The GPT-3 authors encountered this issue and partially removed overlaps from the training data due to a code bug. They propose strategies to mitigate contamination, including encryption and training exclusion controls. Additionally, personally identifiable information, PII, such as phone numbers and email addresses have been found in pre-training corpora, resulting in privacy leaks during prompting. Filtering PII based on legal norms in respective jurisdictions is discussed to prevent extractable models. Section. Pre-training domain mixtures. Our discussion begins with the concept of pre-training domain mixtures. This approach recognizes that including a range of different data sources in the pre-training phase can greatly enhance the model's capabilities. Essentially, we're talking about bringing together various datasets to train the model, a practice that's already quite common. However, we need to explore further just how much data we should pull from each source to get the best results in later applications. Get this mix wrong, and the model could become overly reliant on misleading correlations and underperform when you try to apply it to new tasks. A small experimental model has been developed that optimizes this process, and surprisingly, we've found that even when a data source is given less weight, the final model's ability to handle perplexity, which means uncertainty or complexity in learning, can still improve across all areas. When selecting a data source, it's important to focus on those that will be most beneficial for pre-training. A closer look at the impact of using data from various sources suggests that it is generally a good idea. This approach could potentially be more important than the quality or size of the data, which may support the use of smaller, more diverse datasets for pre-training. Next, we turn our attention to fine-tuning task mixtures, which is the process of optimizing a pre-trained model for a variety of tasks, usually with a limited number of examples for each task. We've seen significant improvements in generalization with a method called multitask prompted fine-tuned language models, or MTLMs, and this requires very little additional computational resources. For instance, a popular approach involves instruction fine-tuning. This involves adding task-specific instructions to each set of input-output pairs. In one specific case, a dataset was developed containing instructions for over 1,600 distinct tasks. MTLMs have also been extended to include multilingual tasks, showing that using English prompts to fine-tune the model can improve results in all languages. However, striking the right balance in the datasets remains a challenge. To address this, tasks are mixed in proportion to the number of examples in each one's tron split. But MTLMs aren't perfect. They can sometimes underperform compared to models fine-tuned for just a single task. This can be due to what's known as negative task transfer, where learning multiple tasks at once hinders the learning of specific tasks, or catastrophic forgetting, where the model forgets previous tasks when learning new ones. It's a delicate balancing act, and the right approach depends on the specific goals of the downstream tasks. We also observe a trend of emulating successful models like ChatGPT by collecting datasets of their outputs and using those for fine-tuning an open-source language model. However, it's important to note that these imitation models may only be good at copying the style, but not the substance, of the proprietary model. So, there's still a significant gap between open-sourced and closed-source models, which highlights a need for further research and better imitation data. Section Summary. Several studies have emphasized the importance of diversity in pre-training corpora, but the optimal mixture of data from different sources is still unclear. It has been found that including heterogeneous data sources in pre-training is generally beneficial, even more so than data quality or size. When fine-tuning pre-trained models on multiple tasks, the balance of task datasets is crucial, as learning multiple tasks simultaneously can hinder the learning of specific tasks and lead to catastrophic forgetting. The right values for balancing task datasets depend on the desired downstream goals. Additionally, imitating closed-source models with open-source models has limitations in terms of content replication, highlighting the need for better imitation data. Section 2.2 Tokenizer-Reliance. The reliance on tokenization. Tokenization is the method of dividing a string of words or characters into smaller segments known as tokens, which can then be input into our model. One common technique is subword tokenization, where we break down words into smaller pieces known as subwords or word pieces. This helps us deal effectively with less common words and words not in the model's vocabulary, all while keeping the number of tokens per sequence manageable to conserve computational resources. Typically, subword tokenizers are trained unsupervised to develop a vocabulary and, if necessary, establish rules for efficiently encoding the training data. However, this need for tokenization isn't without its issues. For instance, the number of tokens required to express the same idea can vary widely between languages. This could lead to a skewed pricing model for API language models, which charge users based on the number of tokens processed or generated. This may result in users of certain languages being overcharged and receiving subpar results, especially in areas where these APIs are already less accessible. Furthermore, inconsistencies between the data used to train a tokenizer and a model can generate glitch tokens. These can trigger unpredictable model behavior, as the embeddings for these tokens are essentially untrained. The need to link the tokenizer and the pre-training dataset also means that any changes to the pre-training corpus necessitate a new training round for the tokenizer. Moreover, it remains difficult to devise tokenization schemes that function well in multilingual environments, particularly with languages that don't separate words with spaces, such as Chinese or Japanese. Existing subword tokenization methods are largely greedy algorithms that aim to represent language as efficiently as possible in terms of the number of tokens used. By their nature, these methods tend to favor subwords that appear frequently in the training data and, hence, are common to many languages. This biases the system towards languages with shared scripts, like Latin and Cyrillic, resulting in suboptimal tokenization for languages that have fewer resources. Section Summary. Tokenization is the process of breaking text into smaller units called tokens, and subword tokenization is a common approach that splits words into smaller units. However, tokenization has drawbacks, such as varying token requirements across languages, leading to unfair pricing for API language models. Additionally, discrepancies between the tokenizer and model training data can cause glitch tokens and require retraining the tokenizer. Tokenization schemes also struggle with non-space separated languages and tend to favor languages with shared scripts, resulting in suboptimal tokenization for low-resource languages. Section: Subword-Level Inputs. The primary method used in language processing involves subword-level inputs. This technique is popular because it strikes a good balance between the size of the vocabulary and the length of the sequence. It works by starting with a set of symbols, such as characters or bytes, that make up the training data. The software then learns rules to merge the most frequently occurring pair of consecutive tokens, or units of meaning, which are defined by the existing vocabulary, into a new vocabulary item. This process is known as byte pair encoding. Byte-level encoding is a variant of this approach that uses byte-level subwords. It's especially helpful for multilingual tasks because it enables sharing vocabulary between different languages. Once trained, this software applies the rules it has learned to break down new inputs into tokens. WordPiece is a proprietary tokenization algorithm used in programs such as BERT. Like byte pair encoding, WordPiece begins with a small initial vocabulary and then extends it by learning how to merge rules and creating new vocabulary items. Unlike the aforementioned methods, WordPiece uses a scoring function to balance the frequency of the pair by the frequencies of the individual tokens, giving priority to common pairs with rare individual tokens. Another method, unigram tokenization, trims down a large vocabulary to a set target size. To achieve this, it uses a unigram language model to calculate a loss over the training data based on the likelihood of a particular vocabulary item being removed. The subwords with the lowest losses are removed to create the vocabulary for the next round of iteration. This technique is probabilistic, meaning that during analysis, it scores all possible breakdowns of a given sequence using the unigram language model, and the most likely one is chosen. SentencePiece is a widely used open-source library that implements several tokenization algorithms, including byte pair and unigram tokenization. It also uses other non-subword tokenization methods like word and character-level tokenization. An alternative to subword tokenization is the use of byte-level inputs. Byte-level inputs can either be used alongside subword tokenizers or used to define a limited vocabulary that can encode all possible sequences. One example of this is the training of a non-subword model called Mount 5 using UTF-8 bytes rather than subword tokens. This has shown promising results on multilingual data. There are models that perform comparably to subword-based models but with less computational overhead. One example is the Charformer, a model that doesn't require tokenization. It learns a soft subword tokenization in latent space, known as gradient-based subword tokenization, from byte-level inputs. Another example is a small-scale, 0.8 billion parameter language model that operates on raw byte-level inputs. There's also the K9 encoder, which has outperformed comparable tokenization-based models. There are also approaches to address the computational costs associated with byte-level tokenization. One method involves breaking down input sequences into local patches, which can be processed in parallel. There's even a method that operates directly on file bytes. In a slightly different approach, there are models that convert text into images and train an encoder model to predict the raw pixels of the images. This line of work provides an alternative perspective on language processing, demonstrating the diverse techniques that can be used in this field. Section summary. Subword-level inputs, such as byte pair encoding and wordpiece, are commonly used tokenization algorithms that balance vocabulary size and sequence length. Unigram tokenization trims a large vocabulary to a target size based on a language model. SentencePiece is an open source library that implements various tokenization approaches. On the other hand, byte-level inputs use byte-level encoding, which can be combined with subword tokenizers or used to define a limited vocabulary. Charformer is a tokenization-free model that learns subword tokenization from byte-level inputs, performing comparably to subword models with less computational overhead. Section 2.3 High Pre-training Costs. We want to talk about an important aspect of machine learning, specifically, large language models, LLMs, the high costs of pre-training. The majority of the budget is spent on pre-training these models, which can take hundreds of thousands of computational hours. This not only incurs a huge financial cost, potentially millions of dollars, but also has a significant environmental impact, comparable to the annual energy consumption of several average American households. Current research suggests that the performance of these models increases in line with increases in model size, dataset size, and the amount of computation used for training. This trend, while promising, is also quite unsustainable. It's often referred to as red AI, a situation where top-tier results are effectively purchased with enormous computational resources. To give you an example, according to some calculations, improving error rate from 3% to 2% could require 10 times more data or computational power. This state of affairs is quite unsustainable. In an attempt to solve these issues, two main areas of research are being explored. One of these focuses on the development of compute-optimal training recipes. As we have mentioned, there is now an abundance of data available for pre-training LLMs, mainly due to the widespread practice of using web-crawled text. Coupled with the advent of transformer models and the appropriate hardware, we have been able to create models of unprecedented sizes. Given that we don't seem to have reached the limits of data or model sizes, the main issue at the moment is the amount of computational power available. So, the question becomes, given a certain budget, how large should the pre-training corpus and model be to achieve the highest training efficiency? One proposed solution is the development of scaling laws. These would describe the relationship between LLM performance and factors such as computational budget, model size, and dataset size. Ideally, these laws would help provide the optimal training approach for any given computational budget. For instance, it has been reported that they could predict the performance of the full-size GPT-4 model using a series of smaller models, requiring 10,000 times less computational power. However, the specifics of these scaling laws, such as the exact coefficients, are still a subject of debate. Some researchers believe that the model size should be scaled up more aggressively than the dataset size to use a given computational budget effectively. On the other hand, others argue that many LLMs are undertrained, suggesting that the number of parameters and data should be increased equally. Further complicating matters, these scaling laws can sometimes function as bounds. These bounds might suggest a tenfold difference in the amount of data to use given a specific computational budget. Additionally, pre-training loss doesn't always correlate well with performance on tasks beyond training. Some researchers argue that when selecting a model size, we should consider the computational resources needed for later use, inference, not just the one-time training costs. They propose that it might be beneficial to train a smaller model more intensely initially to save on larger inference costs later. Therefore, they train various sized models on more data tokens than typically used to achieve the best possible performance for a given model size. One of the remaining challenges is predicting performance using inverse scaling, which we'll discuss later. Since scaling laws were generally formulated in the context of pre-training and hence are separate from downstream tasks, predicting inverse scaling properties remains an open question. Some research indicates that scaling laws might differ for pre-training and downstream tasks. Not only does the model size matter, but also the model shape is significant for downstream fine-tuning. Section summary. The high pre-training costs of large language models, LLMs, involve significant compute hours, costing millions of dollars and consuming energy equivalent to several U.S. families annually. Scaling laws propose that model performances scale with model size, dataset size, and compute used for training, leading to unsustainable practices. Compute optimal training recipes aim to maximize training efficiency by determining the appropriate pre-training corpus and model size based on a given budget, while empirical scaling laws provide insights into the relationship between LLM performance and compute budget, model, and dataset size. However, the exact power law coefficients and the correlation between pre-training loss and downstream performance are still debated. Additionally, considering computation resources for future inference, training smaller models more intensively upfront may offset larger inference costs. Inverse scaling, predicting performance in downstream tasks based on pre-training scaling laws, remains an open question, with model shape also influencing downstream fine-tuning. Section: Pre-training objectives. In this paper, we explore various pre-training objectives or PTOs that we can use to train large language models, or LLMs, in a self-supervised manner. The PTO we choose significantly impacts the efficiency of data utilization during pre-training and, in turn, can reduce the number of required iterations. The three key factors of a PTO are the architecture, how we set up the input targets, for example, the length of the target span or the level of corruption, and the strategy for masking. While these factors can be considered separately, there are popular combinations that consistently deliver good results. We usually use a strategy where all tokens are considered, as depicted on the left side, as it is the most efficient in terms of data usage. This strategy uses context both from before and after the token to be predicted. However, as it takes into account the future context for predictions, it's unsuitable for text generation. That said, it performs well in natural language understanding tasks. In contrast, the next token prediction objective is the most suitable for natural language generation, but it's also the least data efficient as it only considers past context. More recent advances in PTOs aim to balance between these two approaches by providing stronger and more diverse training signals. For example, the prefix LM partly attends to past tokens, increasing data efficiency. Next, we delve into some recently proposed objectives. We denote a sequence of n tokens as x, and write it as x1 to xn. The most basic and still widely used objective is language modeling, or next token prediction. In this approach, we learn the model's parameters by maximizing the likelihood of the next token given the previous ones. Masked language modeling, or MLM, hides a certain proportion of tokens in the sequence by replacing them with a special mask token. MLM is often used for non-generative, bidirectional context models. Here, the model uses tokens both before and after the target token for predictions. This objective allows us to predict multiple mask tokens in one pass, providing a more comprehensive understanding of the context than the next token prediction objective. The METRO, or Model-Generated Denoising Training Objective, further improves the training efficiency of the MLM objective. This method uses an auxiliary language model to predict tokens in the masked positions and then trains the primary model to correct these tokens. Prefix language modeling generalizes language modeling by allowing prefix tokens with a bidirectional receptive field to be added to the input. Span corruption or span denoising refers to a group of objectives that generalize MLM to denoise contiguous sequences of tokens within a given text. This approach often speeds up training because it produces shorter sequences on average. The mixture of denoisers, or MOD, injects diversity by mixing multiple denoising objectives. There are three types of denoisers: regular, specific, and extreme. Each of these types has its own distinct features and use cases, and mixing them can improve model performance. The fill in the middle, or FIM, approach augments the next token prediction objective by shuffling tokens within a document. This strategy fills in the middle based on the prefix and suffix. The meet in the middle objective further extends the FIM approach by enabling bidirectional context to construct a denser, more data-efficient supervision signal. They train two models, one forward and one backward language model, with shared parameters and an agreement regularizer added to the loss to ensure both models agree. These different approaches each come with their advantages and limitations. Choosing the right pre-training objectives and strategies can significantly improve the effectiveness and efficiency of language model training. Section Summary. Various pre-training objectives, PTO, are used for self-supervised training of language models. The choice of PTO affects the model's data efficiency during pre-training. Some popular PTOs include attending to all tokens for natural language understanding tasks, next token prediction for natural language generation, and recent advances like prefix LM and span corruption for increased data efficiency. Section. Parallelism strategies. The considerable scale of large language models, LLMs, makes it challenging to train or even use them with a single accelerator like a GPU or TPU. A widespread solution is model parallelism. Think of this as a divide and conquer strategy where we break down different parts of the model and distribute them across multiple devices. Each device then handles a portion of the overall computation. The results are then combined to produce the final output. However, implementing this strategy synchronously can create an issue. If we run data batches through multiple workers, and each layer of computation depends on the results from the previous one, this can cause significant waiting times and inefficient use of computational resources. An alternative is pipeline parallelism. This strategy blends model parallelism with data parallelism, meaning we distribute not just parts of the model but also parts of the data across different devices. Here, each worker further divides its mini-batch into micro-batches. Gradients across all these micro-batches are accumulated before the model weights are updated. gpipe is an example of this approach, which decreases waiting times and enhances the use of computational resources by dividing each mini-batch into smaller micro-batches distributed across different accelerators simultaneously. The gradients are then synchronously applied at the end. However, issues with these strategies have led to the development of asynchronous parallelization schemes. One such scheme, hog-wild, applies gradients to the local weights on each accelerator as soon as they arrive. This offers better resource utilization than pipeline parallelism, but it suffers from training instabilities due to stale gradients which are based on outdated model weights. Another proposal is N-wise interlocking backpropagation, which is a generalization of end-to-end and local training. Traditional end-to-end training performs a forward pass through all layers, computes a loss in gradients, and then backpropagates through all layers. In contrast, local training performs forward passes through all layers individually and immediately computes a local loss and gradient update. While this offers higher resource utilization, it empirically results in worse task performance. N-wise interlocking backpropagation strikes a balance by performing a forward pass through N layers before computing a loss and updating the parameters of the associated layers. This approach provides better layer communication than local training and higher computational efficiency than end-to-end training. There's also a strategy that leverages a combination of model parallelism and fully sharded data parallelism, FSDP. In FSDP, each device only holds a subset of the model parameters, gradients, and optimizer states, and the parameters necessary for local computations are communicated on demand. This allows highly parallel, high-throughput training across thousands of chips within a single TPU pod. POM, a system that utilizes this strategy, further employs data parallelism to achieve scaling at the pod level, distributing data using the pathway system. Lastly, GS-hard is another solution proposed in parallel research, a model parallelism method that expands the XLA compiler, enabling automatic sharding of models. Section Summary. LLMs are difficult to train or do inference with on a single accelerator due to their large size. Model parallelism divides the model into subproblems and distributes them across multiple devices, while pipeline parallelism distributes both model parts and data parts. gpipe divides mini-batches into micro-batches across different accelerators, while hog-wild applies gradients to local weights as soon as they arrive. N-wise interlocking backpropagation strikes a compromise between end-to-end and local training. POM combines model parallelism and fully sharded data parallelism to enable high-throughput training, while GS-hard extends the XLA compiler for automatic model sharding. Section. Miscellaneous. In our research, we employed a few strategies to expedite the training process and reduce computational requirements. For instance, to kickstart and speed up the training of our 9 billion parameter model, we layered it atop a 4.5 billion parameter model. This reduced the computational effort by a significant 40%, a method that's previously proven beneficial for training smaller language models. When training GPT-3, we steadily increased the batch size from a smaller initial figure to the full value over the course of the training. This approach, borrowed from image model training, helped in streamlining the process. We also applied a strategy known as weight averaging to large language models, LLMs, that ranged between 1 and 12 billion parameters. This saved up to 4,200 GPU hours for a model with 6.9 billion parameters. There are various algorithms designed to speed up the pre-training of smaller models, but their effectiveness when applied to larger-scale models hasn't been proven. Their impact, compared to budget-adjusted training, has been minimal so far. One challenge we face when pre-training LLMs on extensive and diverse text datasets is that these models may not adeptly capture the nuanced characteristics of task-specific datasets. To address this, we fine-tune the pre-trained model parameters on smaller, task or domain-specific datasets. Fine-tuning is an effective way of adapting LLMs for different tasks. This is typically achieved by further training the model on a smaller dataset. Depending on the model's architecture, fine-tuning can be executed directly using a standard language modeling objective, or by adding unique learnable layers to the model's output. These new layers aim to harmonize the model's output with the formats of specific tasks, such as text classification or sequence labeling. However, fine-tuning presents its own challenges. LLMs with billions of parameters have large memory requirements for storing the model parameters, model activations, and gradients along with their respective statistics. The limited memory of devices, like GPUs or TPUs, necessitates access to large clusters with multiple devices to fine-tune an entire LLM. This limits access to those institutions with substantial computing resources. Moreover, although fine-tuning an entire model is effective for task-specific adaptation, it is not resource efficient. Each fine-tuned model must be stored and loaded for individual tasks. This demands keeping each fine-tuned model in memory for every task, leading to a significant overhead. Section summary. The authors of the paper propose using a technique called stacking to train a larger language model, LLM, by leveraging a smaller pre-trained model. They also suggest progressively increasing the batch size during training and applying weight averaging to further optimize the training process. However, a potential drawback of pre-training LLMs on large datasets is that they may struggle to capture the specific properties of task-specific datasets, which can be addressed through fine-tuning. Fine-tuning involves adapting the pre-trained model on smaller datasets specific to individual tasks, but it requires large memory resources and can be computationally inefficient. Section: Parameter-efficient fine-tuning. The focus of this section is on a process known as parameter-efficient fine-tuning, PEFT, which is a method for customizing language learning models, LLMs, for specific datasets or domains. What distinguishes PEFT is its ability to adapt LLMs by changing only a small subset of model parameters, making it more resource efficient. An early technique of PEFT is known as adapters. In this approach, we introduce new, trainable layers into a transformer-based architecture. During the fine-tuning process, only these new layers are updated, while the rest of the network remains the same. According to experimental results across 26 text classification tasks, including the GLUE benchmark, models fine-tuned using adapters perform as well as models fully fine-tuned, but with a key difference: they only update about 3% of the model's parameters. Another strategy proposed for PEFT is to only adjust the model's bias terms during fine-tuning. Bias terms represent less than 1% of the model's parameters, making this approach extremely efficient. Experiments have shown that even with this minimal update, competitive performance is maintained across various tasks within the GLUE benchmark. We recognize three primary frameworks for integrating adapters into language model fine-tuning: Adapter Hub, LLM adapters, and Hugging Face's PEFT library. Some methods have been introduced specifically for larger models, including prefix tuning and prompt tuning. Both of these strategies involve attaching a set of learnable token embeddings, also called soft prompts, to an input at the start of the process. These soft prompts are learned during the fine-tuning stage, and the rest of the model's parameters stay fixed. These soft prompts are efficient to store, as they comprise thousands rather than millions of parameters. However, it's important to note that while fine-tuning the tokens, the network still needs to undergo backpropagation. Prompt tuning has proven its effectiveness, demonstrating that it can learn generalizable representations even with very limited training data. In fact, it can achieve competitive performance when trained on fewer than 100 examples for safety classification or merely 5 examples for multilingual question answering. There has also been research into the use of soft prompts for pre-training and transfer learning across various tasks. One study introduced an approach referred to as EA-3, which scales the activations in individual transformer layers with learnable vectors. Models trained with this method have outperformed fully fine-tuned models on various datasets while only updating 0.01% of the model's parameters. Another approach, called the memory-efficient zeroth order (MESO) optimizer, uses the same amount of memory during the optimization process as it does during inference, avoiding the need for storing gradients or optimizer states. Moreover, It can optimize non-differentiable objectives like accuracy or F1 scores, which traditional gradient-based tuning methods cannot. Yet another method is low-rank adaptation, LoRa, which applies updates to the weight matrices of individual transformer layers as an additive low-rank decomposition. This kind of reparameterization eliminates the need for dense matrix multiplications, thereby increasing efficiency. This method has been further developed for use with quantized LLMs, leading to a significant reduction in memory usage and enabling the fine-tuning of a model with 65 billion parameters on a single 48 GB GPU. To put this in perspective, the authors point out that the regular training of the same model would typically require more than 780 GB of GPU memory. Section Summary. Parameter-efficient fine-tuning, PEFT, is a method that adapts language models by updating only a small subset of model parameters. Adapters, a type of PEFT, incorporate additional learnable layers into a transformer architecture that are updated during fine-tuning while keeping the rest of the network unchanged. Experimental results show that models trained with adapters are competitive with full fine-tuning while updating only a small percentage of the model's parameters. Other PEFT methods, such as prefix tuning and prompt tuning, prepend learnable token embeddings to an input, which are more efficient to store and can achieve competitive performance with less training data. Additionally, techniques like IA, Caret3, Meso-Optimizer, and LoRa are proposed to further improve parameter efficiency and memory usage during fine-tuning. Section. Compute requirements. In terms of computational needs, one of the key challenges with large language models, LLMs, even after applying parameter-efficient fine-tuning, PEFT, techniques, is the requirement for full gradient computation. This high computational demand hampers the application of LLMs in environments with limited resources, such as on smaller devices. One of the problems with these models is the high inference latency, which means they can be slow in generating responses. Two primary reasons contribute to this latency. First, the inability to carry out computations simultaneously or parallelization because the inference process takes place one token at a time. Second, the large memory footprint caused by the size of the model and the temporary or transient states needed during the decoding process, like attention keys and value tensors. Moreover, attention mechanisms in transformers, which have quadratic scaling, also add to the issue of high latency. We will address this topic separately. In an attempt to overcome these issues, researchers have employed various techniques like minimizing the memory footprint and speeding up specific computational operations. While some of these methods might also apply during the training phase, they are not exclusively designed for it. One area of focus has been the attention mechanism in these models. Efforts have been geared towards accelerating this mechanism in two main ways: by making hardware-specific modifications at a lower level, or by making higher-level subquadratic approximations of the attention mechanism. For instance, the multi-query attention method aims to reduce memory bandwidth bottlenecks that occur when generating sequences of tokens in transformer decoder layers. It does this by keeping only one attention head for the key and value tensors. Another alternative method, known as flash attention, reduces the number of input-output operations to speed up computations on modern graphics processing units, GPUs. This method also uses operator fusion to lessen the memory bandwidth bottleneck. Building upon the flash attention method, other strategies incorporate attention sparsity patterns. These involve key, query dropping and hashing-based attention, distributing the computational load more efficiently across devices and optimizing for inter-device communication costs. This enables context lengths of up to 43,000 tokens using multi-query attention. The second line of work aims to improve the computational or memory complexity of the attention mechanism by sparsifying the attention matrix or introducing linear approximations. However, the scalability of some efficient attention approximations has been challenged. For instance, the performer attention approximation has been found to perform significantly worse than the standard self-attention mechanism, particularly when scaled up to larger models. Section Summary. Despite improvements in memory complexity, the time complexity of fine-tuning large language models, LLMs, remains a challenge, hindering their application on smaller devices. LLMs also exhibit high inference latencies due to low parallelizability and large memory footprints. To address these challenges, techniques such as multi-query attention and sparsity patterns have been proposed to reduce memory bandwidth and improve computational efficiency. However, the scalability of some efficient attention approximations has been questioned. Section. Quantization. Let's talk about quantization and pruning, two techniques that are often used after training a model to optimize its performance and efficiency. Quantization is a strategy that reduces the memory used by the model and boosts its processing speed. It achieves this by decreasing the computational precision of the weights and activations used in the model. Two notable implementations of this are NUQMM and ZeroQuant, which employ a non-uniform method of quantization. These systems use special custom-made computing kernels, known as CUDA kernels, to maximize computational benefits. There's a specific quantization scheme known as LLM. Int8 that's quite effective. It allows for efficient prediction using large language models, LLMs, with billions of parameters. This is achieved through the use of 8-bit integer quantization. But when there are outlier features, it switches back to a higher precision without the need for retraining. Another similar approach is used by GLM130B. It stores weights in an 8-bit format and does matrix multiplications with 16-bit precision. Other advanced techniques can compress LLM weights down to just 3 or 4 bits per weight, which can enable a massive 175 billion parameter model to run on a single GPU. These methods are further improved by combining high-precision representations for outlier weights. And a technique called grouped quantization. Pruning is another post-training technique that works hand-in-hand with quantization. It enhances efficiency by removing certain weights from a model without reducing its performance. The key difference is whether the pruning follows a structured pattern or is unstructured. In structured sparse models, dense parts of the model are replaced with assemblies of much smaller but still dense components. On the other hand, unstructured sparse models include weights of zero value, which don't affect the network's behavior and can be left out in theory. However, translating this into practical computation savings on current hardware can be a challenge. Early work on structured pruning of language models was mainly focused on smaller, masked language models, MLMs. One interesting proposition was the LLM pruner, designed to prune large language models in a way that doesn't rely on specific tasks, preserving the model's general-purpose capabilities. The LLM pruner follows a 3-stage procedure. 1. Identifying and grouping interdependent structures within the model. 2. Estimating the contribution of each group to the overall performance and pruning the low-performing groups. And 3. Recovering performance through a parameter-efficient fine-tuning process. For unstructured pruning, a noteworthy approach is sparse GPT, which is quick enough to work with large language models with hundreds of billions of parameters in just a few hours. It can reduce the number of parameters by up to 60% while maintaining similar performance levels. A different technique known as Wanda uses a magnitude pruning method based on the product of the weight's magnitude and the norm of the related input activations. This matches SparseGPT's performance but only needs a single forward pass to prune the network. Both SparseGPT and Wanda can be extended to perform semi-structured pruning, enabling N/M sparsity and achieving corresponding speedups on recent GPUs. Section summary. Quantization is a technique that reduces memory usage and increases model efficiency by reducing the precision of weights and activations. Different methods like NUQMM, ZeroQuant, LLM.int8, and GLM130B use quantization schemes to achieve efficient inference without degradation. Pruning, on the other hand, removes parts of a model's weights without affecting performance. LLM pruner focuses on pruning large language models while preserving their zero-shot capabilities, while SparseGPT and Wanda are fast unstructured pruning approaches that can significantly reduce the number of parameters while maintaining performance. Section. Mixture of experts. Mixture of experts, MO, architecture is a common setup we find in many models. It typically involves a collection of expert modules, each possessing unique weights, alongside a router or gating network that determines which expert will handle a given input. This setup allows for increased efficiency during the inference process, as not all experts need to be activated simultaneously, only a selection of them is used. Moreover, by positioning each expert on a separate accelerator, communication across devices is minimized in model distributed settings. Only the accelerators housing the router and the relevant expert need to converse. One of the early implementations of MO layers in language models was the sparsely gated MOs, SGMOs. In this model, we identify the output from the gating network as G, X, and the output from the ITH expert network as E_I, X, for any given input X. The overall output, Y, is the sum of the product of G, X, and E_I, X, across all experts. Importantly, if G, X, equals 0 for any ITH expert, we don't need to compute E_I, X, which contributes to computational savings during inference. There has been successful work in scaling up an SGMO model to hold as many as 600 billion parameters. This was achieved by utilizing GS-hard, a model parallelism technique that builds upon the XLA compiler. While the SGMO model elects the top k experts for any k greater than 1, the switch transformer, street, architecture simplifies this by only using the top expert, k equals 1. This reduction not only decreases computation and communication demands across experts, but has also been empirically proven to outperform the finely tuned T5 model, resulting in up to 7 times faster pre-training speeds. However, it's important to note that the router function can sometimes lead to unbalanced assignments across experts. To ensure equal distribution of tokens across experts, a linear assignment problem was formulated to optimize token expert affinities. There is also a variant of MO known as SMLP that exclusively uses MLP blocks. This model was successfully scaled up to 10 billion parameters, doubling the pre-training speed, and even outperforming its sparse transformer counterparts. Despite these successes, MO models are not without their challenges. One such challenge is expert collapse, where all experts end up learning the same thing. This is usually due to under-constrained routing functions. In fact, some studies have found that learned expert assignments don't always surpass the performance of random ones. Interestingly, we've observed that the activation maps of standard transformer models often display high sparsity, especially in larger models. In addition, it's been found that post-training, MOification, or transforming monolithic models to equivalent MO models, can double the speed of inference. Section Summary. Mixture of experts, MO, architectures consist of expert modules with unique weights and a router network that determines which expert processes an input, reducing inference time and communication across devices. Sparsely gated MOs, SGMOs, embed a MO layer within a language model, selecting top K experts. Switch transformer, street, architecture uses K equals 1 experts, outperforming a tuned T5 model. To ensure balanced routing, a linear assignment problem is formulated. SMLP, and MO with only MLP blocks, scales up to 10B and improves pre-training speed by 2x. MO models suffer from expert collapse, but sparsity can be implicitly observed in default transformer models, and post-training MOification can speed up inference by 2x.